So a little bit of algebra here. We're going to determine the roots of this rational equation. Okay, maybe it looks a little scary. We're going to do it algebraically because graphing it on a calculator is cheating. Too easy. Dang it. To help explain the method by which we're going to do that, I'm going to go on a brief tangent back to grade 10 math. Really back to grade 9 math. Okay, I'm going to solve a different equation, but the technique I'm going to use is just wave a reminder so we're all on the same page. And then I'm going to go back to the problem that we actually want to solve. Okay, so there's a bunch of different ways you could solve this relatively simple equation, simple for you at this point. You could turn this into a decimal, right? You could just keep it as a fraction and then use flip and multiply. Instead, though, I'm going to get rid of this fraction completely before I do any calculations. And the way we do that is we multiply the entire equation, every single term, by 2. Right? We multiply by the denominator that we want to eliminate. So it'll look like this. It'll be 2 times 3 over 2x plus 2 times 4 equals 2 times 13. Right? Whatever you do to one side, you have to do to the other. That's called preservation of equality. You gotta make sure everything stays equal, so you have to make sure whatever you do to one side, you also do to the other.
So you multiplied everything by 2.
Multiplied everything by 2. So that cancels the denominator that I wanted to get rid of. Right? That was the whole point of doing that. Equals 26, and then we just solve from there. Right? So 26 minus 8 is, what is that? 18? And then divide out the 3 and you get 6. Okay. So it can be useful sometimes to eliminate denominators by multiplying the entire equation by the denominator you want to get rid of. Okay, that's the technique I wanted to highlight because we're going to use it in the equation here, this rational equation. Okay, so turn the page in your notes and let's solve this beast. So again, I've got a denominator here. This time it's got a variable. That shouldn't matter a whole lot because we just basically do what we did last time. We're going to multiply the entire equation, each term, by this denominator. So it'll cancel the x plus 2 in this term, and it will multiply this x and the negative 5 by x plus 2. So it'll look like this. We have x times x plus 2 plus, put it on the left side here, x plus 2 times 6 over x plus 2. Minus 5 equals, oh, missed it. Come on. Minus 5 times x plus 2. Can't forget that. And then all of that equals 0. Okay, so what does that do? Well, it changes the x to x squared plus 2x. It changes this term so that the denominators just cancel each other.
So you just get plus 6.
So you just get plus 6, yeah. And it changes the last term by distributing that negative 5 into the brackets. So you have negative 5x minus 10.
Come on, man.
Anyways. Okay, so simplifying terms, we've got x squared minus 3x minus 4 equals 0. And that's pretty simple to solve, right? That's just normal factoring. X minus 4, x plus 1. Right? So x is either 4 or negative 1. Ooh, I made a boo-boo. One thing I forgot to do. We've got a denominator with a variable, so got to consider non-permissible values, right? So that should be pretty intuitive by now. It's
X can't equal negative.
yeah, right. X can't be negative 2, so we just got to make sure that we check that in the end. Make sure we didn't get anything strange, and thankfully we didn't. Right? Good. So I need you guys to check these answers for me because we run the risk of creating extraneous roots. Right? Remember when we multiply by any term with an x in it, we upgrade the class of the equation. Right? In this case, we changed a rational expression into a linear expression. we changed a linear expression here into a quadratic expression. So we'd run the risk in creating extra solutions by multiplying by x terms. Okay, so just check for me 4 and -1 in your calculators. Put in 4 for x first and -1 and see if they hold. Okay, see if those solutions check out for me. Someone do that for me.
One?
Pardon me?
In the original, right?
In the original, yes.
4 doesn't work.
4 does not work.
Oh wait, it works.
Okay,
Yes,
the way it works. So 4 is good. What about -1?
-1 plus 6. It works.
Yeah, that works too. Yeah. Okay, so they both check out. But I just want to warn you, this, when we get down here, this is not the end. We're not done. We have to check against restrictions, but you also have to check them back in the original equation, because you could have created extra solutions.
Oh,
You understand how that works?
I was graphing.
Okay, so make sure you check your answers at the end, because not all of them will be correct sometimes. So let's just check this on a graphing calculator, further our suspicions that we're right. Okay, so let's graph this. We got x plus x, no, it was 6, over, in bracket, x plus 2, and then minus 5. Is that what it was? Yeah. So we graph, and we're looking for our roots, which are the same thing as what? As the zeros, as the x-intercepts, right? So we're looking for this point and this point. So we can just trace our solutions that we got and see if they're right. So -1, boom, we got 0, nice. And 4, boom, also got 0. Okay, and you can see, yeah, this is just a calculator malfunction. They, for some reason, draw the asymptotes in there when they really shouldn't. Yeah, so this is the asymptote at -2. It even looks like it jogs to the right a little bit here, but prehistoric technology. Oh well. You guys doesn't do it? No, that's nice. Draws the asymptote. So we checked our answers graphing. We're good to go there. What's the relationship between the roots of an equation and the x-intercepts? We just talked about that.
The same thing.
They're the same thing, right?
Why do they ask that?
Because
Can they ever be like
different.
the same? Yeah.
Just they use different terminology at various times. So just as long as you know that they're called roots, zeros, or x-intercepts, it all means the same thing.